Hi there. This lesson is to accompany the problems over heat capacity and specific heat that you are going to be working on today. Hopefully, this will be instructional for you as you go through it. And if you have anything that you need clarification on, of course, please email me or chat, and I'd be happy to help you out with that. Art of the Day. We haven't had Art of the Day in a while. Art of the Day is by Andy Warhol. A giant piece called Shadows. Each one of these paintings, actually screen prints, is 6 feet by 8 feet, and there's like 120 of them in this whole entire series. So it's kind of an overwhelming project from 1978. When I saw it in the in the museum, I was just a little floored at the monumental size of this. Anyway, let's go ahead and talk about specific heat and heat capacity. So heat capacity. What is heat capacity? Well, yesterday in our experiment, you guys saw that if you had different types of metal and you put them into water, even if the pieces of metal were the exact same temperature and the water was the same temperature from experiment to experiment, the energy transferred from the metal to the water was different. It seemed as if each piece of metal, even though they were the same temperature, had a different capacity to hold heat, which is where this idea of heat capacity comes from. So let's define heat capacity and then talk about it. Heat capacity is the amount of energy, the amount of heat, because heat is one form of energy, the amount of heat energy that an object must absorb to increase its temperature 1 degree Celsius. So if you look at my two pictures here, you'll notice that I have a glass of water and I have a lake, Crater Lake to be exact. If I wanted to increase the temperature of each of these samples of water, the glass of water and the lake of water, if I wanted to increase them by 1 degree Celsius, let's say they were 20 degrees Celsius and I wanted to raise their temperatures to 21 degrees Celsius, which one of these would take more heat to do that? Which one has a greater capacity to absorb heat and not change its temperature? Well, hopefully you said it would take a lot more heat for the lake to raise 1 degree Celsius than for the glass of water to raise 1 degree Celsius. And that's because there's a lot more water molecules that you have to heat up to get moving faster by 1 degree Celsius in the lake than there are in the glass of water. So we say that the lake has a greater heat capacity, it has a greater capacity, greater ability to absorb heat without changing its temperature. The water can't gain as much heat without changing its temperature. So heat capacity relates these two things, this idea of heat and the idea of temperature change. So what affects heat capacity? Well, the first thing that affects heat capacity is what we just talked about, the mass of the substance. The mass of the substance is going to affect how much heat capacity the substance has. So that's the first thing. What else? From yesterday's lab, what else affects the heat capacity? Well, hopefully you said the composition, the type of substance that you have. If you look here, I have 3 different types of substances. I have water on the left here, I have a metal in the middle here, and I have sodium chloride on the right-hand side. And each one of these substances, because of the way their molecules or their ions are held together, or atoms are held together, can absorb heat in different ways, because heat causes molecules to start moving faster, and molecules moving faster is what temperature is related to. So some substances can have to absorb a lot of heat before their molecules start moving faster and faster, and some substances gain just a little bit of heat and their molecules or atoms start moving quite a bit faster easily. So here's some values of, I'm sorry, we're not there yet. A lot of times when we're talking about heat capacity, we don't actually want it to change due to the mass that you have. In other words, if we look at water in a lake and water in a glass, each one of those per gram requires the same amount of energy to heat up 1 degree Celsius. It doesn't matter if I have a lake or if I have a glass of water. So sometimes it's a lot easier, instead of talking about the heat capacity of a certain body of water, it's a little easier to talk about what's called specific heat capacity. And this is the one we're going to talk about more often, which is given the symbol C. Sometimes it's just called specific heat. But specific heat is the amount of energy needed to raise 1 gram of a substance 1 degree Celsius. So if I had a glass of water and I took 1 gram of the water out of that glass of water, it would take me the same amount of energy to raise 1 gram of the water 1 degree Celsius as it would take to take, let's say I had the lake, and we take 1 gram of water out of the lake, that would take the exact same amount of heat to raise that 1 gram by 1 degree Celsius. And so specific heat is a little more useful because you can scale it up. In other words, if we know how much energy it takes to raise 1 gram of a substance 1 degree Celsius, if we know how many grams we have, we know how much total heat it would take to raise the temperature of the whole sample. So specific heat capacity or specific heat is usually a little more useful because we can scale it to whatever size sample we have. So the formula for specific heat is C, which is the symbol for specific heat, equals Q, which is the symbol for heat, over M, which is mass, times delta T. Delta T stands for change in temperature. So let's make this explicit. Q is the heat absorbed in joules or calories. In other words, when you put the heat into the water, how much heat does it take to raise that many grams of the substance? So M is mass. It must be in grams. And delta T, delta always means change. And when you find the change in something, it's always your final condition minus your initial. So the final temperature minus the initial temperature will give us delta T. And you can use either Celsius or Kelvin for delta T. The reason for that is because the unit of Celsius and the unit of Kelvin are identical. So when you subtract final minus initial Celsius, you get the same answer as subtracting the final and initial temperature in Kelvin. So the change gives you the same thing, so it doesn't matter which one you use. You can use either one. Typically, you'll be given Celsius. So the units of specific heat are heat over mass over temperature, so calories per gram degree Celsius or joules per gram degree Celsius. It just depends on what unit you use for Q. We will typically use joules, but you can use calories also. So joules per gram degree Celsius. How many joules are required to raise 1 gram of a substance 1 degree Celsius? That's what this unit means. Just to give you some reference, here's some specific heat capacities of some common substances. You'll notice that the metals have fairly low specific heats, and that's because metals heat up very, very easily. Notice aluminum's is pretty high relative to the other two, which is interesting, but they are all below 1. Ethyl alcohol has a specific heat capacity of 2.4. Waters, you'll notice on this chart, by far the highest. It has a very high specific heat. It takes a lot of energy to heat water up, which is also why it takes a long time for water to cool down, because water holds that heat really well without changing its temperature. But that's as a liquid. As a solid, as ice, it has half the specific heat, roughly. Granite is 0.79 and glass is 0.84. So these are some relative specific heats. And just again, to remind you what this means, if you have a chunk of aluminum, let's say 1 gram of aluminum, you would have to add 0.9 joules of energy to raise 1 gram of the aluminum 1 degree Celsius. For gold, you would have to add 0.126 joules of energy to change 1 gram of gold 1 degree Celsius. So the higher the specific heat capacity, the more energy it takes to change its temperature. The lower the specific heat capacity, like gold, the less energy it takes to heat it up or cool it down. So gold heats up and cools down very, very easily. It doesn't take much heat to heat gold up. Water, a lot of heat. It takes a lot of heat to heat up water. I do want to show you one last thing. Specific heat capacities are given in joules per gram degree Celsius, but we also can talk about what's called molar heat capacities, which are joules per mole degree Celsius. And this actually is kind of telling, because if you look at the metals, it looks like they have very different heat capacities, and they do have very different heat capacities. I mean, aluminum is 9 times as much as gold. But on a mole level, because mole atoms are so heavy compared to aluminum atoms, if you look at the molar heat capacities, look at this, 24 joules per mole. So it takes 24 joules to raise 1 mole of aluminum 1 degree Celsius. Gold, 25.6 joules per mole degree Celsius. So metals actually have very similar molar heat capacities, how much energy it takes to raise 1 mole of their substance. So why are the grams so different? Well, remember, atoms have very different masses. So because gold's so heavy, it has a very small specific heat capacity. Okay, but I just wanted to show that to you because I thought that was really interesting. Okay, so let's do a couple of practice problems just to see how specific heat works. So let's say you have 375 joules of heat and you add that to 45-gram sample of some metal and its temperature increases by 5.2 degrees Celsius. What's the metal specific heat? Okay, so how are we going to solve this problem? Well, I'm going to use the guess method. We have the heat in this problem. It is 375 joules of energy. We have the mass of the metal, which is 45 grams, and we have the change in temperature. Notice that it says it increases by 5.2 degrees Celsius. It doesn't give us the initial or final temperatures, but it gives us the change in temperature already. You have to be real careful with the wording on temperatures. So we're given Q, M, and delta T. What's the unknown? Well, the unknown is the specific heat. That's what we're trying to solve for. So I've got my givens, my unknown. Now I need my equation. C equals Q over M delta T. So Q is 375 joules. The mass is 45 grams. And the change in temperature is 5.2 degrees Celsius. So what does this equal? Well, if you do this on your calculator, you will end up with 1.6 joules per gram degree Celsius. And notice where this unit comes from. It comes from all the units in the equation itself, joules per gram degree Celsius. 1.6. 2 significant digits because in our problem, the least significant digits is 2. So would you guess this was a metal or a non-metal just looking at this value? Well, it says it's a metal, but that's a pretty high value for a metal. So I guess it is a metal because it says it's a metal, but that's pretty high value for a metal. Let's look at another problem. What is the specific heat of a material that loses 956.7 joules of energy when a 34.2 gram sample of it is cooled by 7.2 degrees Celsius? Okay, so let's tackle this. Now we got to be really careful with signs. In a couple of lessons ago, we learned about positive always means gain and negative always means lose. This one says it loses this energy. So that means this item has a negative 556.7 joule energy change. Negative means loss. The mass can never be negative. It's always positive, so 34.2 grams. Delta T, it says it's cooled by 7.2 degrees Celsius. Cooled means we're losing temperature. So again, that means the temperature is going down, so negative 7.2 degrees Celsius. And then what are we solving for? The specific heat. So we've got everything we need. If you forget one of the negatives, then you'll end up with the wrong sign in your answer. It won't make sense. C, specific heat, always has to be positive. Okay, so let's go ahead and solve this. Here's our equation, Q over M delta T. Q is negative 956.7 joules. The mass is 34.2 grams. And the change in temperature, negative 7.2 degrees Celsius. If you do that math on your calculator, you will get 3.9 joules per gram degree Celsius. And that's it. So we can solve for specific heats of substances if we know how much heat it takes, how much mass was heated, and how much the temperature changed. Now, there's another way to rearrange our specific heat formula. I'm going to rearrange this. I'm going to get rid of the denominator. So how am I going to do that? I'm going to multiply both sides by M times delta T. I'm going to cross this over to this side. And when I do that, I get Q equals MC delta T. And this is a really useful form of this equation because most of the time when we're using specific heat, we already know the specific heat of the substance. Not always, but a lot of times if you know what substances is, you can look up specific heat on the internet. But Q is what is hard to measure. It's very hard to measure how much heat something has directly, but we can measure the mass of something. We can look up the specific heat of an object, and temperature is very easy to measure with a thermometer. So this form of the equation is one we are going to use most often. Q equals MC delta T. Q equals MCAT. Kind of looks like MCAT, except the A is a delta. Be careful with that. So this allows you to calculate how much heat is lost by an object or gained by an object, or to the surroundings or from the surroundings if we know the mass, the specific heat, and the change in temperature. So let's look at a practice with this equation. So if the temperature of a 25-gram sample of water changes from 22 degrees Celsius to 30 degrees Celsius, how much heat energy did the water absorb? And I gave you earlier the specific heat of water, 4.184 joules per gram degree Celsius, or you could have looked it up on the internet without any problem. So let's go ahead and write down what's given in this problem. The mass is 25 grams. Now we're not given the change in temperature, we're given the actual temperature. So I'm going to go ahead and write down both of these. The initial temperature is 22.0 degrees Celsius, and the final temperature is 30.0 degrees Celsius. It's really important that you get which one's initial and which one's final from reading the question carefully. Because if something's cooling, you'll end up with a negative sign. If something's heating up, you'll end up with a positive sign for delta T. If you switch them, your sign will be off. So be really careful with those. And then specific heat of the water is equal to 4.184 joules per gram degree Celsius. The problem's asking us how much heat did the water absorb. So we're just going to use our new arrangement of the equation. You could use the old arrangement, but that would require more algebra. So we can use the new arrangement. Q equals MCAT, MC delta T. We can plug in each of our values, 25 grams times specific heat, 4.184 joules per gram degree Celsius. And change in temperature means T final minus T initial. So make sure you put them in the right order. T final minus T initial. And so if we multiply all of this together after subtracting that, you will get your final answer of 840 joules. Two significant digits because there's two significant digits in the problem. 840 joules. A lot of times we'll write things in kilojoules, which means move the decimal 3 places. That would be 0.840 kilojoules. Don't be too confused by joules and kilojoules. It just means move the decimal if you need to. So be careful with those units. You'll see both of them often. Okay, so that's Q equals MCAT. Let's do one last problem. If you feel really confident, you can duck out right now. But let's go ahead and do our last problem here. It says we have a 37.5 gram piece of aluminum. It cools from, so temperature initial, 75.2 degrees Celsius to, so temperature final is 22.0 degrees Celsius. The specific heat of aluminum, and I gave this to you on that previous slide, but here it is again, 0.89 joules per gram degree Celsius. How much energy was lost? Q equals question mark. So we've got all that we need in order to solve this. Q equals MCAT. M is the mass, 37.5 grams. C is 0.89 joules per gram degree Celsius. And change in temperature is T final, so 22.0 degrees Celsius, minus T initial, 75.2 degrees Celsius. Notice that this will give us a negative value of temperature because the temperature went down. That's going to give us a negative for Q because the heat went down. It lost energy, so we should end up with a negative Q. That's why we use negatives for loss. So if you do all the math here, you should end up with negative 1,800 joules of energy. The negative means that we lost the energy. Again, a lot of times because our joules are going to be pretty big, a lot of times these could be written as kilojoules instead of joules by moving the decimal over 3 places. 1.8 kilojoules, negative. So that's it. That's all that we have to talk about in this lesson. If you have any questions, of course, please let me know, and I'd be happy to work with you and get through the problem.